Hello, good everybody. So welcome to yet another problem session, solving session with Special Maths Academy. So we're looking at the problem corner for February 2021. So we already did the warm up. So welcome to level one. Um, so we have 8 points, A to H, distinct. Then we have eight circles from those points, and it's given that no 3 points are collinear, and also ABCD is not circular. So the question is, how many collaterals are there? All right, so let's get right into this. So transferring all the way to GeoGebra now. Okay. Yeah, so this is a sketch of what we have. So we have eight circles. So let me just write them here. We have um, B, C, D, E, A, B, E, F. We have C, D, E, F, and B, C, F, G. We also have T, A, B, G, C, D, G, H, A, B, C, H, and finally we have D, A, H, E. Okay, so we have a nice diagram here, but unfortunately, if you try constructing this figure, starting with each of these circles, you see that things are not going to work out so smoothly. So let's analyze what's going to happen. So we have so let's say we're starting with um, A, B, C, D, right? Okay, so they are not on the circle, so just randomly scattered points, not on a straight line, not on a circle. Then we have that these two we have here. So we have that E lies on circle B, C, D. So if you just give a sketch, so let's say we have a let's say B, so C somewhere here, maybe D here. Okay. Then what we have in the first part is just simply that if we draw the circle, um, just give it a sketch. So if we draw this circle, then E just lies somewhere here for now. Okay. And then if you once you have E, you see that this pair of circles kind of defines F, meaning that F is going to be the second point of intersection of ABEF and CDAF. So the other point of intersection is A. So we have A and F common here. So when you draw those two circles, so ABE and circle CDA. So the second point of that section is basically going to be F. So just continue this direction and you see that you get for G, we could see this simply to be, just a moment. So for G, what we see here is this is basically the intersection of these two circles now that we have F. So once you do that, you get G. It's going to be a second point intersection because we already have B for both of these. And then for H, you could also go with maybe this. So this is going to define H. The second point of the intersection of A of those two circles will be A. So we already had A, and the second point will be H. So this kind of like defines F, G, and H, meaning we now have this extra condition, okay, which might follow, which might also not follow. So as it turns out, this condition doesn't follow. So there are special cases when this happens, and that's even true even when you change the position of E. So I'm just going to skip that for now. But when you change the position of E, you see that it's not going to really work well. So what we're going to do is Okay, maybe I should give a sketch to give you a good idea. Just give you a sketch to give you. Okay, so let's just get a sketch. But it's not necessary, but you might want to see what actually happens here. So we have A, B, C, D, random points, so to speak. So let's say we have A, B, C. Okay, and then we have D somewhere here. So we just draw these circles. Let's see, one more circle. Okay, so we have all this, and then now we just pick E, a point on B, C, D, E, on B, C, D. So so we have B, C, D here. We could just pick E, let's say here. Okay, so now to get F, we take cycle A, B, E, intersect C, D, A, which we already have as this circle here. So they meet here. So this is F. Okay, so now to get G, we use BCF. So BCF. So we have that now. And then DAB, which is this other one. So we need to zoom out a bit. So we have G somewhere up here. Okay. So we have G here. And then for H, you could go with any choice. All three are kind of any pair of these three will define H. So just go with the ones we described before. We have A, B, or C, okay, the smaller one, and then D, A, H, E. So that's D, A, E. So D, A, E, we need to draw that. So D, A, E. Okay, so it meets this other circle here. So this is A, B, C up to H. Okay, so what remains now is the final circle. So we need to check if we have that final circle. So since we defined H as the last point, we would look at C, D, G and see if it passes through H. So you see C, D, G, and it doesn't pass through H. So I'm just going to highlight so C, D, G. So just color this red and color H red. So what we want is for H to lie on the red circle. Okay, so we see that if we move E around that circle, in fact, it will never, it's not going to work this way. So it's not really about E, it's more about A, B, C. So maybe by adjusting this somehow, yeah. So somewhere around here, so this works. And interestingly enough, once that works, no matter which place you place E on that circle is still going to work. So there's just some setup about A, B, C, D that you just need to get the rest of the figure right. So there's some condition involved which we're going to investigate later. So let's get back to what we have. Okay. So now moving on. So just gonna erase this. All right. So similar to what happened in the warm up, going to look at potential circles we could have just from 4 points. So now it's not hard to observe that we can't have any 5 points on a particular circle. Because if you have any 5 point on the circle, it's going to force all the circles to be one and the same. Just take for instance, suppose A lied on the circle BC, the circle BCFG, then that means the circle DACF will also be the same as this circle. So we just get a sequence of those stuff going on. So that means D will also lie on that circle, and that will you just keep forcing themselves like that. So you can't have any, and once you have that, eventually you now have A, B, C, D lying on one circle, which is not supposed to be cyclic. So you can have this sort of setup, meaning that we can assume that safely there are no 5-point lie on a single circle. Okay, so same as before, we just look at potential circles we could have. So we already have 8. And similar argument to what we did before, we should be expecting 14 of those. So you can just check the warm-up. So for the warm-up, we had 14 possibilities. So we have 8. Need to check 6. Okay, so we need to just figure out what those 6 could be. All right, so we're just going to write what those 6. So you could just check them one after the other. So we could use, so we have B, E, G, H, A, F, G, H. We have this A, F, G, H. We have D, E, F, G. We have C, E, F, H. We have A, C, E, G, and we have B, D, F, H. So how can you go about this? Well, you could just pick a pair of points that just any pair of points actually. So you could just pick any pair of points. Let's say we pick CD, right? Look at the diagram, the list we have here. We have CD here, CD here, CD here. So that means from the argument we're trying to make, this is all the circles we could get. So we have CD pairing with either BE or AF or GH. We can't have any other stuff because there'll be a repetition in alphabets and that will create 5 points in a circle, right? So we can't have any more from CD. So you could just look at similar stuff. So let's look at BE, for instance. So for BE, we already have CD. So let's check for others. So we have BE here. And that's actually all we have for now. So we have AF. So to know the last possible circle that we could probably have is to just complete this list. So we have GH left. So that's what is to this. So you can just use similar arguments until when you get all 6. Okay, so those are the ones we just need to check if they actually circles or not. Okay, so to do this, we need to, there's some observation we just make briefly. So if you observe, there's some kind of symmetry playing along here. You have that when you like sort of take this map, right, and this other map, so kind of disjoint. So when you do this, basically you just get from one circle to another. So to explain better what this means, if we start with the circle CDE, for instance, then this, moving through this map, what we're going to get, B becomes C, C becomes D, D becomes A, E becomes F. So that means this one becomes circle. And if you continue with that, you get D, A, B, G. So that becomes, so from here, it comes here. And A, B, C, H. So it comes here. This one. It comes here. And it gets back to this after the 4th one. So the same actually happens with the others as well. So in fact, this will come here, this will go here, here, and then back. So that's the kind of structure we have. And by looking at this structure, it means that once you perform this map, the diagram actually doesn't really change because these are circles and they will all remain circles. On the other hand, if you start with BEH, then it's going to map to this one, which now maps to this, which maps to this and back. So what this means is that if we show this is cyclic, for instance, then it automatically means that all these other three are also cyclic and vice versa. So we have that. And then if you look at this, they map to each other. So the same, if any of this is cyclic, then same for the other. So basically just have two things we really want to check. So if one is cyclic, the other is definitely going to be cyclic. So all we just need to check is whether BEGH is cyclic and ACEG is cyclic. So if we have this, then we could plot out the rest. Okay, so to do this, we're just going to use Spalatia that makes this a lot easier to see. So it's called Clifford's circle theorem. So I'm going to use this diagram to illustrate that. But to do this properly, I have to eliminate some things. So I'm going to hide some. So I'm just going to isolate H. I'm going to isolate H. Okay. And this circle here. Okay. So having done that, you see that we have 4 circles. We have 4 circles. And all the circles pass through a common point, B. And then we have 6 other points which correspond to the second point of intersections of each circle. So you could just call this, let's say, circle 1. We call this, let's say, circle 2. We call this circle 3, and this one, circle 4. So G will basically be the second point intersection of 1 and 4. G will be 1 and 3. C would be 3 and 4. F would be 2 and 3. Then A will be 1 and 2. So you see that it's okay, it's remaining 1 more. This is 2 and 4. So you see that we basically get all just different spot. So 2 and 4. So we just get 6, which is 4 combination 2. So that's why we have 6. Now, what the theorem says is that once we have this setup and we look at the circle passing through any 3 points that correspond to three circles. So let's look at, say, circles 1, 2, 3. And we'll see that we have 3 points of intersection, A, G, and F. So if we draw the second circle of this, we draw this circle, right? And we'll do the same for any other triple, let's say 1, 3, 4, like that. So if you draw all those circles, then they are all going to pass through a common point. So I'm going to show that's precisely H. So I'm going to use two circles of 2 of these circles to get H, and then that means we'll have the other circles. So let's do this. Okay. So now let's do this. So we had some before. So in fact, we had this one. Let me see. We had this one and this one. Yeah. So now you observe that we have this corresponding to this circle here corresponds to 1, 2, 4. And this other circle corresponds to 1, 3, 4. So the pass intersects again at it intersects first for at 1 and 4, then again at H. So the other 3 circles, which should come from 1, 2, 3, and also 2, 3, 4, must also pass through H. So we could use some angle chasing to get this, but I'll just use this avenue to make use of this theorem. Okay, so we'll just draw those circles. Just draw those circles. You have so 1, 2, 3, and find them before. So that's this, and this. So yeah, so that passes through H for sure. And then 2, 3, 4. So for 2, 3, 4, we have 2, 3, 3, 4, and 2, 4, which is down here. So we have this. So this gives. So this gives 2 circles. So we have 2 pairs of cyclic points. So what this relates to, we just need to confirm which circles this is. So this one is C, E, F, H. That's the one here. And then this other one is A, F, G, H. Yes. So we have this one. So in fact, just getting one of these, like we mentioned before, is enough. So that means all 4 are cyclic. So it's just a matter of applying this theorem maybe from a different perspective. So for example, if you want to get for E, E, G, H, so you can look at that as mapping from AFG to BEH, meaning that you move, instead of focusing on H, you move one step, so focus rather on E. And then all the circles will now meet at C. Yeah. So once you eliminate the other circles to make it clearer, then you see that you get BEGH. So once you get one, you have the others. So altogether we have plus 4 for now. So it still remains 2 more. So remain 2. And those 2, they go in pairs as well, A, C, E, G, and the other one. So just need to check one, and that's it. I'm just gonna erase this. And we had some circles before, and we're going to bring them back. And also, draw the other 2 circles we just got as well. So that's B, E, G, H. So B, E, G, H. So we have that circle. Then D, E, F, G. So D, E, F, G. So we have this circle. Okay, so now since we have all these circles, I'm just going to blend them in. So you see that there's some nice symmetry going on, perfect symmetry. So we have, okay, so we have this setup, which is very symmetric, especially if you consider the mapping we used. So that's the basis for the symmetry. So now I want to consider A. So I want to look at A, C. So if you observe this, I color this in a particular way. So the purple color, the purple points, those are the ones we want to look at. This. And then the other would be the green ones. So if one is cyclic, then the other, just to make sure you can. So this one is not, it's not that hard to see. So this bit here is equal to this bit of the green. This one is equal to this one, and we have this equal to this from all those circles we get. So final one, let's say this is equal to this. So when you sum these two and the other two are G, you get if you get 180, then automatically that means this two sums to 180 as well. So one is circle, the other one is definitely circle. So we're going to prove by contradiction that we can actually have this circle. Clearly it's not looking like a circle, but maybe that's just this diagram. So how do we do this? Well, so since it's very symmetric, we are going to assume we've not really labeled these points yet. So the idea is that we can draw a circle that covers, that contains those points, and shrink that circle until it touches 3 points. So let's say touches is that D, E, F. Then since we have D, F, then there's going to be a 4th point on that circle. So that's G here in this case. So they may not necessarily have this naming, right? So maybe I should just draw based on a different sketch. So we have 3 points at the extreme, circle that covers every other point. So every other point is within this circle. There's going to be another point here. And if you pick any 2 points, you remember we could draw 3 circles. So already, if you pick this point and this point, so we can draw 2 more circles passing through both of them. So they're going to cut inside this circle, something like this. And these other points will also, when you pair them, they can also get 2 more circles. And the intersection points here would correspond with the other 4 points we need. Okay, so once you have that, then since you can also get 2 more circles from these other pairs of points, something that looks like this. So they must align in this particular way. So once you've done this, then basically you just have, so just assume we have the diagram we had before. Okay, so this diagram now, you see that since B and H, or if you want to go with A and C, so since A and C lies within a bigger circle, which is this one, okay, so if you look at this angle here, the angle at E, is going to definitely be less than the structure just established. It's going to be less than the entire angle at F from D and F. Okay, yeah, the entire angle at E from D and F. So this is less than that, and similar to those at E at G. So this is also less than the other one. Now, if you look at the bigger ones, they sum to 180. So that means the smaller ones definitely cannot sum to 180. So this we get our contradiction. So that means we could only get at most 12 circles, similar to what we had before actually for the bonus question. So yeah, and the other 2 circles cannot exist. So we only have those circles. All right, so that brings us to the end of this level 1. So you're going to move to level 2 next. So make sure to like and subscribe so that you could just get more content. So I'm getting to level 2, and there are some things we could have done here that we're going to do there because of what it takes. So just stay tuned. All right, thanks for being here. See you in the next one.